Hello, my name is Avik Chaudhuri, and I'm the person standing between you and a coffee break. Let's start it again. Okay, so I'm going to introduce you to PyTorch export, a mechanism that enables sound whole graph capture for PyTorch programs, something that builds on the technological breakthroughs of torch.compile, except that here we are no longer talking about compiling just in time as your program runs, but rather completely ahead of time. All right, so there's a short talk. I'm going to keep it fairly high level. 3 things to cover: why we need export, how we built export, and finally, what export looks like. All right, so let's start with the why. Why does PyTorch need a sound whole graph capture mechanism? The short answer is because it's often necessary. So remember that with torch.compile, there's a lot of back and forth typically with the Python runtime. So you call a function and we grab the bytecode, and then we compile it into a subgraph. But if we run into something that we cannot compile, then we would typically fall back on the Python runtime and let it rip for a bit, and then come back, resume compilation, and then get another subgraph. So torch.compile actually relies on these fallbacks. But now imagine environments that must be completely Python-free. For example, devices that have various hardware constraints, or servers that don't want anything to do with Python. God knows why. What do you do in those cases? Besides, whole graph capture is often desirable. Imagine that you have a representation of the entire computation to be performed by your model. And now think about all the special purpose optimizations that you want to apply on it, right? You might also not only optimize your code, but also bake in specific assumptions in your code that a general purpose compiler would never consider, right? So the possibilities are endless there. All right, so let's say you're sold on whole graph capture. Why do we need soundness? Well, hold on now. We're talking about capturing a model once and for all based on some measly example inputs, and then we are going to run it on possibly many different inputs in the future. So what's to say that your code won't crash? And what if it does? Like, imagine debugging a runtime failure so far away in space and time that you don't even remember when and where you compiled your code, right? So it's a nightmare. So let's say you do find the root cause eventually, and they fix your code. Now you have to go through the entire process all over again, deploy a code, and then what? Like pray? So what do we mean by soundness anyway, right? So put simply, it means that if you feed in valid inputs through your code, you get correct outputs. We can infer what valid inputs mean based on your example inputs. So we generalize this slightly. If that's not enough, if you want more generality, you tell us exactly what you had in mind, right? As for correct outputs, it basically means whatever the original code would have produced given those inputs. All right, so that's enough about the why. Let's go into how we built export. Well, it was easy and it was hard. The easy part is that torch.compile exists, and it has some truly remarkable pieces of technology inside. The hard part is that we are going against the grain of PyTorch. In some sense, we are going against the spirit of eager. So we are talking about graphs now. What are graphs? So we have to be careful, right? Usability has to be a top concern. How do we ensure that you even get an exported model? Standardization has to be a top concern. How do runtimes ensure that they can run and then keep running your exported model, right? So these are new things to think about. All right, so we basically reuse Dynamo for whole graph capture. You give it example inputs, it traces through the code, and it gives you back a graph. That's easy. The catch is that you might have to rewrite code sometimes. And this is partly because of how tracing compilers work. For example, control flow. We'll only ever take one possible path through your code, and we'll in fact complain if it's not clear which path to take, right? So if you want to capture more paths through your code, you have to use special control flow operators like cond. To guide you, we have built a database of examples called ExportDB, which we hope to grow over time. These contain a bunch of examples of supported and non-supported use cases, things that are expected to work and expected to not work. And when you get errors, we would typically link to these examples so that you can know how to fix them. Right? So there's something that we are going to continue polishing over time. And overall, we are committed to make it as easy as possible for you to export your code. Let's talk about soundness now. All right, so Dynamo was designed to be sound. What I mean by that is that not only does it generate code based on the traced path that it takes, but it also returns so-called guards that encode the conditions along the traced path. These conditions guard the correctness of the code. They are necessary conditions. And these guards are very easy to check by a machine, but they're not designed to be human readable. And that's fine, because in eager mode, we basically use them to decide when to recompile. When we check these guards, when they fail, we recompile, right? So the human is never in the loop. For export, though, we want to focus on conditions on the shapes of input tensors. These are called shape guards. And we want to use these shape guards to establish a contract with the user. So for that, we first simplify these guards to sufficient conditions that can be understood by the user. And then we verify these conditions at compile time. This process can lead to errors, but these errors will always have actionable error messages. And then once this process finishes, we would turn this contract into runtime assertions. We'll also assume static types by default, static shapes by default, by which I mean that the shapes of the future inputs have to match exactly the shapes of the example inputs. And this is just like static type inference. But sometimes that's not enough, right? So just like you might want to add generics to your program, you might want to export your model with dynamic shapes. Let's take a concrete example. Suppose you have a matml operator in your code, right? So rather than specializing it to expect and return 4x4 tensors, because that's what you got when you were tracing through with your example inputs, you might want to generalize that part of your code to expect tensors of shape A cross B and B cross C and return a tensor of shape A cross C. So you need those symbols, right? All right. Hopefully that's enough whetting of appetite. Shall we finally see what export looks like? All right. So as I said before, we compile assuming static shapes. So what you do is basically pass to export a model or any callable really, pass in some example inputs, and you get an exported program which you can then run on other inputs as long as the shapes are exactly the same as the example inputs. So nothing much to see here really, which is the whole point, right? Often this is all you need to do to export your model. And in fact, this is how we automatically manage to export a whole bunch of models in our open source benchmark suite. And of course, you might get errors when it's not possible to capture a whole graph, in which case your errors would point to the examples that I just talked about. You can look at those examples and fix your code, but often that's about it, right? But sometimes you might want to generalize your code to inputs of different shapes, in which case you would use dynamic shapes, right? So a very common use case is when you have a batch dimension that can vary over time. So what you do is you create a dimension called batch. This is just a symbol, really, and you use it to create a dynamic shape specification for your inputs, which you pass to your export call. And now, boom, your exported program can be called on inputs with different batch dimensions. All right? So this is the API for using dynamic shapes when exporting. All right, so finally, let's say that you get an exported program. Well, the whole point of this exercise was to do something with it. And often you would want to write your own custom passes on this exported program. Underneath, it is just a vanilla FX graph with a bunch of extra information like source level metadata, static and dynamic shapes, and so on, right? And you can do whatever you want with this graph. You can replace ops. You can lower to your own favorite IR, and so on. Or you might want to give away the task of writing these custom passes to some backend, right? So you want to enforce a front-end, backend separation. Well, you would save and load your exported program, much like you would save and load a PyTorch model, right? Except that here we are not just talking about the model weights, but also the model code and all the extra information I just talked about, and also version information. Finally, something that people working on backends might be interested in. By default, your exported program will have operators in the full 8n offset, functionalized to simplify transformation. Backend authors can target a core subset of these operators to maximize coverage. And it's a simple API call to convert an exported program to this subset. We call it run decompositions. And you can also use this to plug in your own specialized operator implementations. Say you have hardware, special hardware to do convolutions. Well, you can tell the API to avoid decomposition of that operator, and then you can replace it with yours. There's a lot more to talk about. For example, we have support for custom operators as well. But that's basically what I want to say about export today. Please try it out. It's available through Nightly's. There are no guarantees about stability yet. We're working on it, and hopefully we'll do a formal release soon. Just so you know, this is not just a prototype. We have been using export successfully inside Meta for a while. In fact, it is powering AI inference on Meta RL devices, Reality Labs devices. It's already shipped with Ray-Ban's Meta smart glasses, and it's coming to Quest 3 VR headsets soon. It's also driving a whole bunch of our next generation serving use cases. And this is all made possible through integrations with Execute Torch and AOT Inductor. You might have heard talks about these throughout the day. We are also seeing broader community adoption through integrations with TensorRT and XLA. And we're also excited to collaborate with industry leaders like Apple, ARM, and Qualcomm on various integrations. So that's it. Please let us know your experience using export. We are here to listen, to support, and to improve. Thank you, and happy hacking. So I can take questions, or as I said, I'm standing in the way of you and coffee. Yeah, go ahead.
Do you support backward inside export?
Yeah, we're working on it. The export IR has a backward graph as well. But yeah, stay tuned. We have some way to go before we can completely support it. Any other questions?
How do you do the function matchup for inserting flow control? What do you use to disambiguate the various paths?
So as I said, you have to rewrite code sometimes. So if you want, you're saying how do we even decide which path to take?
Maybe I misunderstood. I thought you did rewrite.
No, the user has to rewrite code. And we have these special operators like torch.compile, which you can use to basically specify both branches, and then you'll capture both paths. But yeah, we do decide to take one path based on whatever your example inputs are giving you. And we try to kind of abstract that symbolically, but we can go only so far. Yes? Yeah, right now, you have to you have to capture the whole thing. In the near future, we might be thinking about composability a little bit. For example, we have heard use cases where you might want to capture a subgraph and then maybe transform it and plug it into another larger part, which you export separately, and so on. So we have to flesh out that story as well. Yeah. All right. Thank you.